Welcome students for the chemistry lecture. And last time you have learned the Gibbs-Helmholtz equation. And the Gibbs-Helmholtz equation, it is the relationship between enthalpy, entropy and Gibbs free energy of the system. Let us revise that Gibbs-Helmholtz equation once again. You know, the Gibbs free energy mathematically defined as G, it is equal to H minus Ts, where H is the enthalpy of the system, T is the absolute temperature and S is the entropy. And all of you know enthalpy is defined by the equation, and that equation is H, it is equal to U plus Pv, and in your book they have written internal energy by notation capital E. Therefore, enthalpy it is equal to E plus Pv, where E it is the internal energy of the system and P is the pressure, P is the volume. Then substituting equation number 2 in equation number 1, we get G it is equal to E plus PV minus Ts. Let it is your expression number 3. And differentiating this equation on both sides, we get dg it is equal to du plus pdv plus pdp minus tds minus sdt, and let it is our expression number 4. Then from the first law of thermodynamics, here for reversible process we can write internal energy dE, and here they have written du, it is equal to dq reversible plus dw. If the work is of expansion type, then dw it is equal to minus p dv. Therefore du it is equal to dq reversible minus p dv. We have replaced dw as a work of expansion, dw as a pdv. Therefore, we have du it is equal to dqr minus pdv, and let it is our expression number 5. Then by the definition of entropy change, we have ds it is equal to dq reversible by t. Therefore, the product of t into ds it is equal to dq reversible, it is equal to t ds, and substituting this equation number 5 and 6 in equation number 4, we get dg it is equal to dq reversible minus pdv plus pdp minus dq reversible minus sdt plus pdp, and here there is a minus term, this one is the plus term, they cancel each other, and here we have plus dqr, here we have minus dqr, these two terms get cancelled with one another, and we have here this plus term pdp minus sdt. Therefore we get dg it is equal to pdp minus sdt. Understand, this equation is an important equation. The small change in free energy, it is given by the product of volume into pressure change or change in pressure minus entropy of the system into temperature change or variation in a temperature. Remember, this equation is the most important equation. dg it is equal to pdp minus sdt. It is our expression number 7. Then at constant pressure dp it is equal to 0. That means in this equation this term it becomes 0, and we have dg it is equal to minus sdt. It is our expression number 8. Then consider a system in which the following reaction occur at constant pressure. Suppose we have A as a reactant and it gives B as a product. Let S1 and S2 be the entropies of the reactant and product respectively, and G1 and G2 are the free energies of reactant and product respectively. Then from equation number 8 we can write here dg1 it is equal to minus s1 dt and dg2 it is equal to minus s2 dt. Therefore, dg2 minus dg1 it is equal to minus s2 dt minus s1 dt. And here we take this as a d in a bracket g2 minus g1 it is equal to s2 into dt plus s1 into dt, that is d of delta g it is equal to minus s2 minus s1 into dt, and d of delta g we can write as a delta s minus delta s into dt. Therefore, from this expression we can write delta s it is equal to minus d of delta g by dt. Delta s it is equal to minus d of delta g by dt. But we have delta g it is equal to delta h minus t delta s, and substituting the value of delta s as d of delta g by dt. Here substituting equation number 9 in equation number 10 we get delta g it is equal to delta h plus t in a bracket d of delta g by dt at constant p, and let it is our expression number 11. This equation 11 is called as Gibbs-Helmholtz equation, and this term d of delta g by dt at constant p is called as temperature coefficient of free energy change. Then the applications of Gibbs-Helmholtz equation. This equation is the Gibbs-Helmholtz equation. It is applicable for calculation of delta G for all processes occurring at constant pressure. It helps to calculate EMF of the reversible cells. Then one can use this equation for the reversible cell for a reaction if free energy change at two different temperatures are known. These are the few applications of Gibbs-Helmholtz equation. Okay, this is the Gibbs-Helmholtz equation, and it gives the relationship between enthalpy of the system and Gibbs free energy and temperature coefficient. Then the next point, the Klaperon equation and the Clausius equation. Then here the scientist Clapeyron he used or applied the second law of thermodynamics to the phase change, and all of you know the phase transformation or phase transition or phase equilibrium. It is nothing but the there is equilibrium between two phases. Suppose the phase change, if we have a solid and we hit that solid, it will get melt at its melting point, and there establishes a equilibrium between solid and its liquid. Then in case of evaporation process, that means if we hit the liquid at its boiling point, the liquid it will get converted into its vapor, and there establishes a equilibrium between liquid and its vapor. These are the examples of phase transition, and the scientist Clapeyron he applied the second law of thermodynamics to the phase transition. So we derive the Clapeyron-Clausius equation here. The various processes which involve the phase transitions are vaporization, evaporation, condensation, fusion, etc. In all these processes, there is a new substance formed. That means solid, it will get converted into liquid. Liquid, it will get into gas or vapor. These are the phase transitions. When substances involved in these processes are in pure state, then after some time these processes reach equilibrium at constant temperature and pressure. Thus, we say that phases are in equilibrium with each other, and this is possible if delta G it is equal to 0. That means the entropy of a final state and entropy of an initial state, these two entropies are the change in free energy. That means the free energy of initial state and free energy of a final state. These two free energies are same. That means the phases are in equilibrium with each other, and this is possible only if delta G is a 0, where delta G is the free energy change accompanying this process. Then consider the following equilibrium between two phases. Suppose we have this A phase is a liquid phase and B phase as a vapor phase. That means when we hit A phase liquid, it will get converted into its vapor. Okay, that means B phase is our vapor phase. This is the vaporization process. And if we consider Ga and Gb are the free energies of A and B per mole respectively, then delta G at constant temperature and pressure, it is equal to Gb minus Ga. That means the change in free energy of this vaporization process. The free energy of vapor phase minus free energy of liquid phase, and it is equal to 0 at equilibrium. That means at equilibrium delta G at constant temperature and pressure, it is equal to 0. Therefore, here we can write Gb it is equal to Ga. Thus, when two phases of the same single substance are in equilibrium at a given temperature and pressure, then their molar free energy is same in each phase. Then the Klaperon equation. Here, consider the following equilibrium between two phases A and B of the same substance at a given temperature. Here, phase A, it is in equilibrium with phase B. As already you know, phase A, it is our liquid phase, and phase B, it is our vapor phase. Here, let Ga, Gb are the free energies per mole of A and B per mole respectively. Then at equilibrium Ga it is equal to Gb. Now if the temperature is changed from T to T plus delta T, that means if we temperature changed from T temperature to T plus delta T, we have increased the temperature by this delta T, then the free energies of A and B will also change to Ga plus dGa and Gb plus dGb. Therefore, we can write this equation Ga plus delta Ga it is equal to Gb plus delta Gb, and as we have Ga it is equal to Gb, from equation number 1 we can write dGa it is equal to dGb, and it is our expression number 2. But dG we have equation number 7, as already we have seen dG it is equal to phi dp minus s dt. It is our equation number 3. Therefore, we apply this equation for the phase change and we write dGA, it is equal to phi A dP minus SA dt. And you know, this A, it is our liquid phase. That means volume of liquid into dP minus entropy of liquid into dt. And here dGB, it is equal to phi B dt minus SB dt. And you know, this B, it is the vapor phase. That means volume of vapor into dP minus entropy of vapor into dt. And let it is our expression number 5. Then substituting equation number 4 and 5 in equation number 2, we get here phi A dP minus SA dt. It is equal to phi B dP minus SB dt. And we can write this equation as phi B minus phi A into dP, it is equal to SB minus SA into dt. Therefore, we can write this dP by dt, it is equal to delta S by delta phi. And the significance of this equation, the rate of change of pressure with the temperature, or the effect of pressure on the melting point or boiling point of the process. It is equal to delta S by delta phi. Okay, then again we know delta S, it is equal to delta H by T, where delta H is the molar latent heat of phase change occurring at temperature T. Therefore, we replace this delta S by delta H and we have the Klaperon equation as dP by dt, that is rate of change of pressure with temperature, it is equal to delta H upon T in a bracket delta phi. And this equation number 6 is known as Klaperon equation. You know, this equation is known as Klaperon equation. Then the Clausius, he modified the Klaperon equation assuming that the vapor behaves ideally, and he modified Clausius modified the Klaperon equation. So we will see here the Clausius-Klaperon equation. Here, consider the following type of equilibrium between two phases of the same substance at constant temperature and pressure. And this is the vaporization process. That means there is equilibrium between liquid and its vapor phase in forward direction, and in backward direction there is a equilibrium between vapor and its liquid. If Ga and Gb are the free energies of liquid and vapor state respectively, then we can write Ga equal to Gb. If the temperature of the system is changed from T to T plus delta T with the corresponding change in pressure from P to P plus dP, then Ga becomes Ga plus dGa and Gb becomes Gb plus dGb. After the change, again the two phases remain in equilibrium. Okay, so we can write Ga plus dGa, it is equal to Gb plus dGb. But since Ga equal to Gb, hence we can write this dGa, it is equal to dGb. Okay, let it is our expression number 2. Again, we have this equation dG, it is equal to phi dP minus S dt. Hence, we can write dGa, it is equal to phi A plus phi A into dP minus SA into dt. Expression number 4, and dGb it is equal to phi b dp minus sb dt. We have this as a equation number 5. Then from equation number 2 we have here phi a dp minus sa dt it is equal to phi b dp minus sb dt. Therefore, we taken this phi b minus phi a, that is volume change into dp it is equal to, this is the entropy change into dt. That means again we have dp by dt it is equal to delta s by delta phi, and we replace delta s by delta h upon t. So we get dp by dt it is equal to delta h upon t in a bracket delta phi. And you know this equation is the Klaperon equation. In terms of liquid vapor equilibrium, the equation can be written as here dp by dt it is equal to delta h phi upon t in a bracket volume of vapor minus volume of liquid, where delta H phi is the molar heat of vaporization of the substance, phi that is volume of vapor, and phi L volume of liquid. Here Clausius modified the Klaperon equation suggesting the following things. The first thing, that is for vaporization and sublimation, volume of vapor it is a very large as compared to the volume of liquid. Therefore, volume of liquid can be neglected, and assume the vapors to behave ideally. And applying these two assumptions, the Clausius modified the Claperon equation. So, applying the above modification to equation number 8, we get dp by dt it is equal to delta h phi by t into delta phi. For 1 mole of vapor behaving ideally, we can write p phi it is equal to RT. Therefore, phi it is equal to RT by P. Let equation number 10. Then substituting equation number 10 in equation number 9, we get dp by dt it is equal to delta h into p upon RT square. Let it is our expression number 11. On rearranging equation number 11, we rearrange this equation 11 as dp by p it is equal to delta h v into dt upon RT square, or we can write this d ln p by dt it is equal to delta h v upon RT square, and this equation is known as the Clausius-Clapeyron equation. If P1 and P2 are the vapor pressures and temperature T1 and T2 respectively, then integrating this equation number 13, assuming that delta H phi to remain constant over the temperature range, we get here integration of this d ln p it is equal to delta h p by r. This is the constant, and integration of 1 by t square into dt within the limit t1 and t2, and here the limits of this are p1 and p2. Here we get integration as ln p2 by p1 it is equal to here minus delta h v by r in a bracket 1 by t2 minus 1 by t1. Therefore, we can write ln p2 by p1 it is equal to here with plus sign delta h v upon r in a bracket 1 upon t1 minus 1 upon t2, and changing this natural log to the log base 10, we can write here log P2 by P1, it is equal to delta HP upon 2.303 R into 1 by T2 minus 1 by T1, and this equation is called as integrated form of Clausius-Klaperon equation. And here we see the applications of Clausius-Klaperon equation. This equation helps to calculate delta HB if P1 and P2 and T1 and T2 are known, and one can calculate T2 if P1, P2, T1 and delta HB are known. This is the Clausius-Klaperon equation, integrated form of Clausius-Klaperon equation. Log P2 by P1, it is equal to delta HP upon 2.303 R into 1 by T2 minus 1 by T1. So the problems based on this equation, they may be asked, okay, to solve the problem. You may study this well, okay, and the next point we will see later on. Thank you for your patient listening.